Hello. Now, the very last subproblem. Determine an infinite family of distinct pairs of rational numbers s and t with this range, with this restriction about range, that satisfy the equation in B. The equation in B is already found. It basically is this, right? And we have to determine an infinite family of basically infinite numbers. We have to prove that there exist infinite numbers of st that satisfy the equation in B, and we've got this restriction. But I can tell you that this restriction is not a great deal. It's not the hardest part. That is because, I mean, although it is just between 0 and 1, it looks narrow, but we can just move s by a little bit, and if s is moved by a little bit, shifted by a little bit, then a t will change by a little bit as well, and still we can get another pair of s and t. So it is not hard to get infinite pairs of s and t within this range, 0 and 1, between 0 and 1. This range is, this one is wide enough, because we can just shift them by a little bit, and by a little bit. But the hardest part lies here, in fact. Rational numbers, all right? Why is this hard? That is because if we check this, or maybe let's check this one, it looks like a quadratic equation. I mean, if we consider t as a constant, and we fix t, and we solve it for s, we are solving a quadratic equation, and very likely we will, end up with something with a square root. And under the square root, we might have a bunch of things. And a square root doesn't usually guarantee a rational number, right? Square root 2, square root 3, these are non-rational numbers. In very few cases, a square root is a rational number. And that's why this problem is hard. We will have a square root, and we have to prove that still we can make some construction, create something so that under the square root, there could be infinite numbers of rational numbers. Infinite numbers of rational numbers. Yes, that's what we are doing in this problem, basically. So we're gonna see the square root and try to see if we can, we can construct something so that the thing under the square root is a rational number, and this construction is kind of infinite. We can always use this kind of construction and get as many rational numbers as we want. Okay, so I've just talked about why this problem is kind of hard. Okay, not this part, not because of this part, just because that both of them has to be rational numbers. Okay, now let's start. Let's carry out. I don't even think we now have a plan, but let's just have a look at what might appear under the square root sign. All right. Oh, let's see. S squared plus 4ts. We're gonna solve for s, so it's just a fixed t. This is it's a 40 minus 2. Wait, okay. S squared plus 4t minus 2s. That is on the other side. The whole thing, everything with a t is moved to the other side, and now 2t minus 1 s plus 2t minus 1 squared. This is a minus t squared plus 2t plus 2t minus 1 squared. This is a s plus 2t minus 1. Looks not too bad. On the other side, it's a 3t squared. It is a minus 4. Okay, minus 2t 1. Okay, that's what we have here. And of course, we will have two situations to deal with. Situation number 1, or case number 1, the bunch of things within the bracket is a non-active thing. It follows that s plus 2t minus 1 is square root 2. Now we see something under the square root, right? And case number 2, the things within the bracket is negative, and it is in fact negative the square root. And the thing under the roof within the square root sign has to be a rational, and that is why this problem is a bit challenging. Okay, now let's give a closer look to the bunch of stuff under the square root sign. This is a this is the thing, and this has to be k squared, where k is rational number. All right, and this doesn't always happen, and we have to prove that there are infinite t's that can give a k square where k is a rational number. And if I check this, when I check this, I see something like it's quite close to something squared, and maybe I can. So this give me a thought that maybe we can later use the difference of square formula. So basically that's what I mean. I see a square. This is what I see on the left side, and on the right side is just a k squared, right? And this is a 2t squared, and that one is actually t minus 1 squared, and this is a k squared. All right. Now, if we move that over, we get square minus square, so we can apply the formula of difference of squares and see if we can have something. But for now, let's make some assumption here. K cannot be a 0. That is because this is a squared and this is squared, so the left side is non-negative, and in fact it cannot even be 0, because if t is 1, this part is 0, but this is not 0 anymore, and if t is 0, this is 0, and that part is not 0 anymore. So the whole of the left part has to be just a positive, strictly positive. So let's just assume that k is a positive rational number. All right, and then let's carry out what we have just mentioned. K minus k plus. That's it, right? So this is rational, and the t is rational, and k has to be rational. We just need to prove that we can find as many as we want rational numbers that satisfies. So what can we do? Everything actually has to do with the coefficient here, 2, the coefficient 2. I mean, I can split this into 2 parts. 2t squared is a at times bt. And at, I can just suppose that it is a k minus t. So the first bracket is just at, and the second bracket, here, is just a bt, all right? This actually is my construction. This is my creation. And of course, if this is the case, then a times b has to be 2. And let's just assume that a and b are both positive, all right? A times b is 2. And in that case, of course, what we want is that a and b are both rational numbers, and that is not a big problem. It's not a problem at all, right? 2 numbers, they are both rational, and the product of them is a 2. Of course, we can have infinite numbers of a and b. So to find a pair of a, b is not a problem at all. We can give as many as we want. Okay, that's it. Basically, we have already kind of solved this problem. This one is effectively finished off, but we have to just solve something, and maybe later we will deal with the range thing. Now, for now, we know that the construction is done. We can have as many pairs of AB as we want, and A times B is 2, and AB are both rational numbers. All right. So the square root is already dealt with. It's no longer a challenge to us. And now let's kind of solve for t and k in terms of a, b, and it's just a sum and difference problem. So k is plus, all right, a plus b divided by 2 times t. T takes a bit longer, but t minus 1 is b minus a divided by 2 times t. Okay, and then that means that 2t minus 2 is b minus a times t. Sorry, it is just 2. It's a constant here. And move it over, that is 2t minus 2. It is, yeah, I think, yes, it is. Okay, and then what do we do here? Okay, move over. And this is a 2 plus a minus b. T is 2, meaning t is 2 over 2 plus a minus b. All right. Once we've got this, we can plug it in again, and this goes to 2 over 2 plus a minus b. This is a plus b and 2 plus a minus b. That is it, right? And let's make some assumption as well. For now, let's see the restriction here. T, according to the problem, the t we want has to be not over 1. It has to be lower than 1 or equal to 1. Meaning here, t minus 1 cannot be anything positive. It could be 0 or negative. Meaning minus t minus 1 is actually going up. It is going up. And this one is going down. So this actually is the larger number among the two. Or in other words, A has to be larger than B if both A and B are positive. Now, so we have this. A is larger than B and both of them are positive and the product is 2. So A is over square root 2 and B is lower than square root 2 or equal. Okay, here we go. That's it. A is bigger than B. That's what we're talking about. And it follows that the denominator is a positive because a minus b is a positive. And the denominator here has to be positive. Okay, this is the one restriction we will need later. But let's just keep it in mind. Okay, now what? Now we've got k. We've got t in terms of a and b. And we actually have a relationship of a and b. So b is none other than 2 over a, but later we're gonna use this. For now, let's just make do with a and b, both of them. And now, of course, we're gonna solve for s, because this problem is not talking about k. The problem is talking about s. But s has to do with k. You see, the square root thing here is a k, and the whole thing here is a negative k. So we can just solve s once k and t are known. So let's move on. S is a negative 2t plus 1 plus k. Okay, what's that? I'll just plug this in. Negative 4, 2 plus a minus b plus 1 plus k. What is k? Here we've got k, okay, which is good. A plus b over 2 over a minus b. Okay, and now I need another sheet of paper to move on. And this is put everything together. Negative 4 plus 2 plus a minus b. This is a one part. Okay, and then copy. Here it is. And this is a 2 over a minus b. B and b are gone. So we've got 2a minus 2. 2a minus 2. That is it. That is s. Okay, let's keep it here. And in this case, I mean, this is case 1. And how about case 2? Okay, the same. S is... case 2 here. S is negative 2t plus 1 minus k. Okay, this is a k again. And the things in front are... Okay, let me just do it anyway. In fact, they are just the same. I mean, the first two terms are the same. So this is a minus a plus b and 2 plus a minus b. Okay, now let's move on to the paper down here. It should be 2 plus a minus b, the common denominator, and then minus 4 plus 2 plus a minus b this time. And it leads to... a is gone, there's no a anymore, and there's a minus 2b, and it's a minus 2. Minus 2b minus 2. That's it. Okay. So, see. This is another s. This is s in case 2. Okay, this is a case 1 s, and this is a case 2 s. All right. And let's copy the other two, right? Let's just copy them. What is t? T is 2 over 2 plus a minus b, okay? And what is k? K is, we don't need k anymore, just t will do. And what is the range thing? Let's see it here, over here. Okay, both are positive. S is S is lower than t, or no larger than t, and the t is under 1 or below 1. So it is, okay, let's just copy it first. Now we have to determine the range thing, right? But before that, there's one thing I want to mention. This part is actually a negative thing. That is because the denominator is a positive. A is bigger than B, as we said. A is bigger than B. So the denominator here is positive, and the numerator, the top, is negative. You see, it's a negative something minus 2. So it is a negative thing, meaning the whole thing is a negative. Negative divided by positive, it's a negative. S is a negative, and this actually is not allowed. S has to be a positive, right? S has to be a positive. This is not what we want here, meaning the whole of case 2 can be discarded. We can say bye to this. This is not what we want, so forget about this, and let's just stick to our case 1. All right, so half the problem can be discarded, so half the burden is gone, which is a good thing, in fact. Okay, and then let's check these inequalities one by one. Okay, first of all, S has to be positive. And as I said, the denominator is positive for sure. So the top has to be, the numerator has to be positive. 2a minus 2 is a positive, meaning a is more than 1. And this is for sure because a is more than square root 2 is 1.4 something. Of course, a is more than 1. So we don't have to worry about the first part. This one is already guaranteed. Okay, this is already guaranteed. And now let's check the second part. S is lower than t. It's no more than t. It doesn't go over t. S is 2a minus 2 over a positive number. And t is 2 over a same positive number. That basically means that 2a minus 2 has to be lower than 2. That gives that 2a is smaller than 4 and a is smaller than 2. Okay, this gives a upper bound. Okay, it could be equal because this could be equal. So everything could be equal. A cannot go over 2. See, here we have to add something. So a cannot go over 2. A is equal or lower than 2. And that's it. Now we've got another restriction in terms of a with regard to a. Okay, that's it. The second part is done. We have kind of solved it, and this would guarantee this. And finally, t smaller than 1. Of course, this is for sure. I mean, because you see, a minus b is a positive thing, as I said. It's a positive thing or it's a non-negative thing. So the bottom here, the denominator is no lower, no smaller than the numerator. The base is slightly bigger, and the top is smaller. So the t has to be a fraction under 1, or maybe it's just a 1. In some case where a equals b, but in most cases it is lower than 1. But anyway, this is guaranteed. Okay, so the range thing is totally solved. It's totally dealt with. There's nothing else we need to worry about. Just to stick to this, all right? And that's it. Of course, there's I mean, if a is lower than 2, then b has to be over 1. That is because a times b is 2. So maybe we can rewrite this. And over 1, all right? Because a times b is 2, and that's it. This comes from this. And okay, now let's just rewrite s and t, because we cannot submit our solution with both a and b. Okay, we'd better we'd better stick to just one variable. Which one? I can choose any one. So maybe just a. Okay. So what do? Then b, in this case, b is 2 over a. Plug it in, and that's it. So we're almost there. Plus a minus 2 over a, right? And some simplification, 2a squared minus 2a, it is 2a plus a squared minus 2. Okay, this is basically s. And how about t? T is 2, and 2 plus a, minus b again, it's 2 minus a, and 2a, and this is 2a plus a squared minus 2. Okay, that's it again. So, yeah, I think that's it. We have got s and t, and a could be any number, any rational number. A could be any rational number, all right? A could be any rational number within this range. And as long as a is within this range, the inequality here is totally satisfied. It is true, and the result, the A would result S and T, and see, check the form here. Actually, both S and T would be rational, and of course they satisfy the equation which we derived from the previous problem. I mean, this one. So this problem is solved. I mean, we've given a proof, and we have constructed an infinite family of S and T that satisfies. Okay, finally, there's one thing I need to clarify. This is my solution, all right? I've just got them. And if you check the official solution, if you read the official solution online, and you will see something that looks like this. This is the S and T given by the official solution. And this is the S and T given by me. This is my solution. They look not actually the same, right? You check the denominator, you check the whole structure of things, and you see it's just not just a substitution. They look different. And what is going on here? Okay, to tell the truth, they are basically the same. We are doing the same thing. And I just want to show this, okay, as a kind of a clarification at the end of this video. So let's check the official solution here. Okay, one thing to keep in mind, this k has nothing to do with the k we used when we deal with the square root, all right? This k is something belongs to the official solution. It has nothing to do with our solution. It's just a variable k. It's a variable, and in the official solution, S and T are they look proportional to each other. I mean, T is just a k times S, right? They have the same denominator, and on the numerator, it is just it's just S times k. So in the official solution, k is actually T over S, T to S, the ratio, it's a ratio. And how about our solution? In our solution, what is T to S? Let's just copy and see 2a squared minus 2a. Okay, that's it. And after that, we get 1 over a minus 1. Okay, it seems that maybe there's something to do, I mean, maybe there's something going on between the official solution and my solution. What if I substitute the k in the official solution with this fraction thing, and see if we can derive my S and my T? If that is the case, meaning, okay, basically me and the official solution are doing the same thing. So, okay, I think just the S will be enough. Just let's just plug this in and see if we can get S, all right? So let's move on here. In the official solution, S is 2k plus 2 over k squared minus 4k minus plus 1, and that is this is a k for now. Okay, let's just plug it in. Copy. Plus 2 are 4 times, and there's 1, and just simplify. 2a minus 1 plus 2a minus 1 squared times a minus 1 squared on both the denominator and the numerator. So it is 1 plus 4 a minus 1 plus a minus 1 squared. Open them up and see what we have here. 2a squared, it is minus 4, sorry, it's minus 4 and minus, plus 2, so it's minus 2a. And it's minus 2, and it is plus 2. A minus and plus 2 are gone, so there's nothing, there's no constant on the top. And on the bottom, it is a squared minus 2. Okay, so it is a squared minus 2 and plus 4. This is a plus 2a. Okay, and how about a constant? It is 1 minus 4 and a plus 1. So 1, 1, 2 minus 4, it is negative 2. Okay, this is what we derive from the S in official solution. If we replace k with 1 over a minus 1, we reach this, okay? We end up with this. And come on, here is my S. You see? If you compare them, they are exactly the same. Have another look. Here, right? We go all the way down from the official solution, plug it in, so it becomes something like this. And in my solution, this is my S. They are exactly the same thing. So meaning, basically, me and the official solution are doing the same thing, just that I used a, and the official solution used k. Again, the k has nothing to do with my square root thing, okay? It's just a variable in the official solution, and it's a substitution. In fact, it is a substitution, but it's quite hidden. If you substitute k with 1 over a minus 1, finally you will come from the official solution and end up with my solution. You can also do the other way. Okay, that's all for this problem. Bye.